Illustration on two-way ANOVA. We should all be pros by now, but we're not, and because we still got a lot to learn about this stuff. So I've chosen an example that doesn't really create much drama, but I did it for a reason to illustrate a couple of extra things. Okay, so guys, again, two-way ANOVA illustration. And we're going to get into something called effect size and power. And if you've ever really paid much attention to calculating a test statistic, the test statistic is created by taking an estimate that we call the point estimate divided by the standard error. Well, the standard error component always has a sample size component. So you can show that your test statistic can always be inflated, and again, think it through, bigger test statistics have lower p-values. So your test statistic can be inflated by increasing the sample size. Now let's just go back here and let's keep it really, really, really simple. And let's just think back when we back in the good old days when we just had a test statistic of oh, I don't know, let's just take something of this nature. That's about as simple as it could get, just for a one sample t-test. Well, it should be made pretty clear that if we can make this thing smaller, then we make our test statistic bigger. And when we make our test statistic bigger, we get lower p-values. Well, if you hold this, and this constant, it should be pretty easy to see that as you, say, go from n equal 10 to n equal 20 to n equal, just keep letting n increase, you're going to make the denominator smaller. But when the denominator becomes smaller, obviously your test statistic gets larger and it creates a lower p-value. Now, what statisticians realized years ago is that's kind of a weird situation. So they came in with what we call effect size. So think of effect size as just being a way that we can compare or examine the impact of our independent variables on our dependent variables, kind of controlling for the sample size implication, or the sample size effect. Okay, so guys, in a two-way ANOVA, our independent variables are factor A, factor B, and the interaction of A cross B, and our dependent variables, whatever our measurement is that's quantitative. Now, effect size calculations, you get it for two-way ANOVA. You get into a variety of different effect sizes. There's one called eta squared. You also get into an adjusted eta squared, but there's one called Cohen's F effect, which is really easy to calculate, and it's got a pretty straightforward interpretation. So I kind of prefer it. So guys, there are the formulas for the three effect sizes for the factor A, factor B, and the interaction effect. Okay. Now, what does this mean? Well, if we get a value that's about 0.1, then we have a weak effect. There's not much impact on that dependent variable. On that independent variable on the dependent variable. If we get a Cohen's F around 0.25, then we have a moderate effect. And if we get something 0.4 or higher, we consider that to be a strong effect. Okay? After we calculate the effect size, we want to examine the power. And remember, power is just the probability of rejecting a false null, which is usually, typically, what the purpose of the test. Guys, if we get a power above 0.80, then we're considered adequate to good power. So I want to run through an illustration with you here. I've chosen a data set which I chose carefully because I wanted a particular outcome to happen. So what I've done down here is I have my data set. And I have no earthly idea why my computer is not working. There we go. So I've got my data, which is given like this, and it's given in cell format. So we've got two factors: factor A, factor B. Factor A has 3 levels, and of course factor B has 4 levels. This is a balanced design because each cell count is 2. And we have a total sample size, obviously, of 24. Now, what I've done over here to the right is I've put this in Excel format. So I don't need this anymore. So I'm going to save my computer a little bit of processing space. I'm not going to save this, and I'm going to now focus the attention on the Excel format. Now the first thing I'd want to do is I'd want to come in and save it appropriately. We should know by now that we save as. Name it something. I've named it problem. I've put it to my desktop and I've saved it as a CSV format. So I hit save. It's going to go through a lot of wacky stuff. It's going to make you feel like you're not doing something right, but just hit continue and make it happen. So now I'm going to shut this down because I no longer need Excel, because I don't need to save it again because I've already saved it. And on my desktop, you'll see that I have problem in CSV, in the format CSV. Now I'm going to go into R and make some magic happen. Okay, so first thing, I want to set my working directory. I want to get my data. I want to attach my data. And I don't care how long you've been doing this, you're going to want to see your data. Just make sure it's there. Now, the first thing we'd want to do, more than likely, since we've got our factor A and factor B as letters, I have no reason to believe that this is not going to treat factor A and factor B as categories or as categorical data. My measure is clearly going to be quantitative. If, for example, we just had factor A as 1, 2, 3, and 4, well, in this case 1, 2, 3, and factor B is 1, 2, 3, and 4, again, R is going to see that as a quantity. So you'd have to set that as a factor, but I don't think we have to do that in this situation. We can always tell by our ANOVA printout if the degrees of freedom are correct. Then we know that R has seen the factors as we want R to see the factors. So the first thing I would want to do here is I'd want to go fit, and I'd set up my ANOVA, and I would do measure over factor A cross factor B. Now when I do fit, I'm going to get a reduced version of the ANOVA table. It gives me the sum of squares for factor A, factor B, the interaction, and the residuals, which we call the error. And you can see the residual standard error down here is 0.86. Now, what I want to do, though, I want to do summary. I want to get the complete ANOVA table, and I get that here. So what I see is I have a situation where my two main effects are not statistically significant, and my interaction effect is not statistically significant. So really, I'm kind of ready to throw the baby out the bathwater here, in that not much has actually happened. Okay. Now, actually, I set it up like this on purpose, to be honest with you. I wanted to come up with a model that was not dramatic and didn't have much going on, so we could examine this effect size in this power analysis. Now, the next thing I'd want to do probably is I'd want to look at the interaction plot. And I'm always going to put the factor that's smallest first. And when I do that, I'm expecting to get lines that are parallel, because that's what that's the indication of an interaction effect that's not statistically significant. And what ends up happening here is I get just the opposite. Clearly, I don't have lines that are parallel, which tells me I've got something going on. Something going on that should be investigated more closely. So next thing we may do is do a Tukey HSD and do this over fit. And this is going to allow pairwise comparisons. So I go through and look at all my pairwise comparisons, and if you think about it, really the interaction is just a difference of differences. And that's, if you go back and look at the previous video where I gave you the overview of the marginal means plots, that's essentially what the interaction was all about. But as I examine everything down through here, I have no pairwise comparison, if you will, which is statistically significant. So what I'd want to do next is I'd want to examine the effect size. Or not the effect size, but examine the effect. So first thing I want to do is I want to do the effect for factor A, and that is the square root of the number of factors for factor A minus 1. Factor A had 3, so we're going to multiply by 2, times the F value for factor A, which if we go back up to our ANOVA table, we'll see it's 1.775. And we divide that by our total N, which is 24. My effect for B is going to be the square root of 4 levels minus 1, so 3, times the F for factor B, which is 1.531. Divided by 24. And then my effects for the interaction. Guys, remember the interaction degrees of freedom are A minus 1 times B minus 1, so we should have 6, which we do. And we have a very low F statistic of only 0.4, so we're going to have 12 times 0.4 divided by 24. Alright guys, my effect size for A is 0.38, which is a large effect. The effect for factor B is 0.43, which is even larger. And the effect for the interaction is 0.44, which is even larger. So the effect size being large, again, going back to what I told you earlier about the interpretations, we said anything above 0.40 is a strong effect. But it seems like we don't have a strong effect because our interaction, our marginal mean plots, and our pairwise comparisons aren't showing any interaction effect. So what I need to do next is I need to calculate power and make sure that I've got adequate sample size to where I can detect a difference or detect the impact, the statistically significant impact of a interaction or my factor, make sure I've got enough power to. I'm looking for a pencil here, guys, so I can write something down. Well, I guess I'm going to go back and forth. So what I like to do, I think one of the best, the easiest power is one that I've downloaded, and I'll highly recommend that you download it. Okay. And it's called GPower. Now, if I open up GPower, what this allows me to do is quite a few different calculations. The first thing I want you to do is to select central and non-central distributions. And obviously I hope, or at least I hope you know by now, that we're doing an F-test. And then it'll come over and ask what statistical test are we conducting, and we have fixed effects with main effects and interactions. So the default is what we need. And what we want to do here, first of all, is let's do a Posthoc, which will compute the achieved power that we have. Now, the effect size that we had for factor A was 0.385. Well, we will get over there, I think. You love the spinning wheel. Okay. So the effect size we want to calculate is 0.385. We want a type 1 error rate of 0.05. Our total sample size is 24. The degrees of freedom from the numerator. Guys, this is always going to be the degrees of freedom for the total. So if we go back to, I hate to do this because the computer's running so slow. Well, okay, so the degrees of freedom for the total is going to be the sum of the degrees of freedom. So we have 12 plus 6 plus 5 is 23. So you can always remember the degrees of freedom for the total is just going to be the sample size minus 1. Number of groups are 2. And we're not into covariates yet, so we'll control for that, or put up at a 0 there. Now, if I hit calculate, you'll see that the power that I have is only 0.09. Adequate power is 0.80. So I essentially, because of my small sample size, have virtually no chance of rejecting a null if it's false. Now, what I can do now is I could go back up and do a prior and compute the required sample size given certain information. So I've got the same sample size, I got the same effect size, I have the same alpha value, but I want to achieve a power of 0.80. Numerator is the same number of groups. And if I come down and hit calculate, you'll see that I need a total sample size of 166. So considering that I have a design of 12 cells, and if I want to keep a balanced design, I would need the next biggest number that was equally divisible by 12 to achieve the power that I need. So right now, and again, this is kind of cherry picked. I chose this example to make a point. And the point is we don't have adequate sample size really to construct the ANOVA appropriately. Now, if we go back to the interaction effect, Well, don't we love the spinning wheel? Well, all right. If we go back to the interaction, we'll see that we had an effect size of 0.447. So let's go back to the power calculation. And so the effect size for the interaction, the power we desire is 0.8. Numerator, everything else will be the same, right? And do the calculation. You can see that we would need a sample size of 127, so the next biggest number above 127 is divisible by 12, which I think would be 144. No, actually it'd be 132, right? Is the sample size that we would need. So guys, that was pretty much the intent of this video, to talk about power. So get adequate power before you start your test, and that way you don't get into kind of these dilemmas with the statistical significance of interactions not lining up with what we see in our marginal mean plots and so on and so forth. So guys, that's all I got. This will be the final video before our first on-campus session. So have a good one.